There was a problem in the early days that that CCS wasn't really recognised by the UN as a mitigation option. It was sort of parked in research, and we amongst others put a lot of effort into sort of trying to educate the UNFCCC and IPCC in particular that that wasn't correct, and this led to the start of this activity, the IPCC Special Report on CCS, which started in 2002 really and finished in 2005 when it was finally published. And it did make a significant contribution to CCS deployment because it led to CCS being accepted by the UNFCCC as a mitigation option. So it took it out from the park status in research and it put it very much into this is a technology that needs to be included in future assessment reports. It very much set out the technical status of CCS as of 2005, and really we hadn't got a lot in those days. In a sense, there was a lot of research going on, but we really only had two projects, Sleipner and our own IJGGC Weyburn CO2 monitoring storage project. Those were the only two sort of large-scale projects we could point to at that time. But I'm glad to say that a lot of things have changed since then. The special issue was aimed to update the IPCC SRCCS. We finally published 17 technical papers on the progress made. We solicited 20, but not all passed muster, I'm afraid, and we hope that they will flow through in the past. And the takeaway message that we're putting out is that considerable progress has been made in all areas of CCS R&D in the last 10 years. And if you want to go to the journal, if you haven't been to it already, there's the URL. And Elsevier have very generously allowed this papers for free to download at quite a cost to them, I think, until the 31st of December 2015. So they're very much aware of the point of this journal, its focus, and what its contribution. So thank you very much to Elsevier. We released it in September, and of course there was a deliberate aim there so that it was in the public domain before COP21 in Paris, which will be in a couple of weeks. And we've published recently a short summary of this, which will be circulated at COP, which is a 2-page summary of this document for policymakers themselves to digest. And you'll be able to find that on our website shortly. Here are the 17 papers, which you probably can't all read, that have been produced so far, or that are contained in the special issue. They cover all the system, capture, storage, transport, I'm afraid, was missing, monitoring, risk assessment, environmental impacts, costs. We included bio-CCS, legal and regulatory developments, and public developments in public communications. These are all areas where we felt there had been considerable progress in the last 10 years. I'd like to acknowledge the efforts of everybody. In a sense, there were 105 authors who contributed to this issue, and they referenced 3,000 papers. So that was no mean task. Reviewers, in any time I speak about the journal, I have to thank the reviewers. They are the unseen help and assistance without which we couldn't actually produce the journal. And I'm really thankful to those reviewers who number something like 400 or 500 who help contribute to actually allowing us to complete this on time. I wasn't alone in this. I had 3 co-conspirators. That was Carlos Abernades from CIC in Spain, and in fact I have to give Carlos the credit that he was the person who thought of this idea first, and then we mutually took it on board. Stefan Baciu, who's now retired from the journal, I'm afraid, and I wish him all the best in his happy retirement, and Charles Jenkins from Australia. And I'd like to give, I've mentioned Elsevier, but I'd also like to thank Katie Eve, who helped us work through this and gave us tremendous support in helping to publish this in the latter stages, and working with Elsevier to help pull this off. And get us a very good promotional deal. So thank you, Katie. As much as what we included, I think the issue is what we didn't include. And there were certain things that were in the original SRCCS that we discounted here for various reasons. And one of those was system modelling work, because that is now very much in the assessment reports. And if you've read the 5th assessment in your report, you will have seen that they show quite categorically that if you don't include CCS in the models now, that you're going to have a much higher mitigation cost globally. And bio-CCS is also a critical part of that. So where we've dropped out of that, the 5th assessment reports have picked up that mantle and are still promoting CCS. We didn't cover emissions accounting. That was very much a fledgling issue there back then in 2005, and in a sense has really been supplemented by the IPCC guidelines on emissions accounting that came out in 2006. Ocean storage we didn't cover madly because the research in that area is curtailed. Mineral carbonization we didn't cover because we regard this as a niche application, and there's been little progress on some of the key issues like the environmental issues and costs associated with this option since the SRCCS. CO2 utilization, this is the U in CCUS. We didn't cover. It's now very much covered in a separate new journal in the Elsevier range. So there's a journal of CO2 utilization if you're interested. We didn't cover it because it's still a big question out there. Is it really a mitigation option, or is it just if you make a product in one area and you burn it or use it in another, like methanol, is that emissions leakage? That jury's still out. Utilization may be a way in which we can progress CCS deployment, or at least capture deployment, and in sort of industrial regions in the short term, but in the long term we have to look at it. Is it really a mitigation option? I indicated CO2 transport. This is a paper, unfortunately, that we didn't get through here. It was a gap that we need to fill. And we also had a paper that was looking at covering the whole aspects of CCS safety that unfortunately didn't pass muster, and we will look to replace that in due future. And if you look at the discussion or the announcement by the recent the appointment of the new Korean chair of the IPCC, he points to CCS safety issues as an issue that is still out there, and this is one that we will look to cover in the future, and I'll explain why or how in a while. I'm sorry if I croak and cough through this, and I hope I will make it to the end. If not, Sian's going to have to stand in for me, but she's grimacing, but I do hope to make it through. If we look at the different capture options, Ed, what is the journal saying? What is the review report saying? Well, we made the point that post-combustion capturism was mature in industry. At the time of the IPCCS, it was used very much in the ammonia fertilizer industry and in many other industry sectors. And it was mature at a scale. And there's been significant advances in scale-up in 10 years, both in R&D and in deployment at scale. And we now have the first boundary dam as the first power sector demonstration of post-combustion capture, and that's been the subject of an earlier webinar. There's been a lot of progress on the development of new solvents and new solvent-based processes, hopefully which we now see them flowing through the pilot plants and through the test centres, which I think are critical to the development and deployment of CCS in the future. The test centres are playing a critical role. And we've seen a lot of developments now in absorber design, modelling and simulation, again, which will feed into future PCS developments. So there's been a lot of progress in this area. In terms of Oxyfuel, again, significant advances at the R&D scale. We've had the 35 megawatt pilot plant in Schwarzepumpe that operated and ended its operational life. There's a new 35 megawatt plant being built in China. We've had the Calide project, so a lot of demonstration at well above the sort of pilot scale. And it's now sitting there waiting for demonstration. And Of course, everybody had hoped that the first demonstration would be at FutureGen in the USA, but that's not going to happen. So we're now pinning our hopes on White Rose, the White Rose project in the UK being the forerunner of demonstrating CCS, oxy-based CCS. But that's not to say it hasn't got any applications. Quite the opposite. It's very well suited, we're seeing, to industrial applications, and that was never considered in the SRCCS. In fact, industrial CCS was not an issue in those days. We were purely focusing on power generation. There's been a lot of technology transfer into the industrial CCS applications of oxyfuel combustion. We're seeing oxy deployed in fired heaters. We're seeing oxy pilot plants on cement equipment by ECRA in Europe, just to name a few. And what is really emerging as an option, and a technical review that we've just completed, and one that will be technical analysis we've just completed, and one that will be subject to another webinar in a few weeks' time, is oxy-fired cycles. They are demonstrating high efficiencies. Although there's a lot of proponents of this technology, and maybe some would say that the proponents have over-egged it, one of the options of this work was to say, is that right? Can we see the sort of high efficiencies that they were quoting? And certainly we can see efficiencies comparable to existing natural gas combined cycles with CCS, and with proprietary additions that there's a good possibility they'll become more efficient than NGCC with CCS. Some of the other advantages we're seeing in them is low water usage, and also a very compact plant scale on plant's footprint, in a sense, which is going to be very valuable, I think, in implementing these plants in the future and deploying them in practice. Pre-combustion capture, or IJGGC, well, yeah, we know it uses commercially proven gas equipment. Gasification technology has been around for many years. We're close to the first demonstration of this deployed as a CCS option at Kemper County in USA. That'll be in late 2016. And we know that it can be deployed in industrial applications like chemical production and iron and steel manufacture. And many of these, like methanol production and fertilizer production, produce very hot, pure CO2 streams, which could be effectively captured. And there's a lot of deployment of this sort of technology with high purity CO2 being produced in China, for example. And so there's opportunities there in the future for what are always been deemed the sort of issues of low-hanging fruit. And there's been a lot of research on alternative configurations on water gas shift process, and that's been a key R&D topic and remains so in the future. So it's developments of a proven process. A lot of people are talking about second, third generation capture systems as being the route to significant cost reduction and reduce energy penalties. And in the last 10 years, we've seen a lot of literature now, technical literature and research, and we now have a substantial body of technical literature that's been published in the journal, in other journals as well, other chemical engineering journals, on these new, more novel systems. We've seen that some of them have now increased their technical readiness quite considerably. They've gone from TR1s and 3s up to sort of 5, 6s, etc. And these are the sort of calcium looping, the solid sorbents, polymeric membranes, and we're seeing deployment of these around at various points around the world. We're seeing polymeric membranes being deployed at the Norchem project in Norway, and so we're looking now, and we're looking to see some form of technical proofing at pilot scale, and hoping to see some of these technologies developed again and tested at the test centres around the world. And again, I stress the importance of the test centres, the Technology Centre Mongstad, the National Carbon Capture Centre in Birmingham, Alabama, in the USA, to name just two, as critical in bringing these technologies on and proofing them, so we know that they are technically capable of the potentials that the research work suggests they are. So this is going to be a big area, I think, of development in the next 5 to 10 years, and who knows, the subject of another journal update in 10 years' time. But not, I don't suppose I'll be around for that one. CO2 storage. There's been a lot of work on the knowledge base development in deep saline formations, and really most of the research published in IJGGC has been on deep saline formations. But this review was much bigger. It wasn't just IJGGC, included papers from SPE, APG, AAPG, etc., etc. And we still see the same issue, that it's really the research is focused on deep saline formations. CO2 ECVM has dropped away as a topic. It was a topic of interest in the SRCCS. Storage in shales is an emerging topic. And where we have seen injection projects in gas and oil fields, these have largely not involved research on storage aspects, but more involved in monitoring developments. A lot of monitoring activity on these projects, like Snøhvit, like Sleipner, although Sleipner has done a lot of internal research on the storage of efficacy. And these will come out in the monitoring paper summary. We have sort of been criticised that we didn't do a lot on CO2 EOR. My standpoint on this is that CO2 EOR is a commercial technology, and there's a lot of commercial papers published, well, a lot of papers published that relate to the commercial side of CO2 EOR, but we're really interested in the technical research side of it. And we haven't seen a lot of papers that talk about how CO2 is stored in the reservoirs. Certainly not a huge body of literature that we would have expected, and certainly not the same quantity as we have in deep saline formations. But we reference back to an earlier issue, an earlier special issue, which is in volume 16, that was issued in 2013, which covered the IEA GHG Weyburn Midale CO2 monitoring and storage project. And we used that as a base and said, can we actually do anything more substantial than that? And the answer we found came out with was no, not at this time. So we haven't taken CO2 EOR further forward. In storage itself, the subjects that have had the most progress we've seen is storage efficiency, CO2 plume and pressure evolution. That was an unknown topic in the SRCCS, and we've now seen not only more acknowledgement of that as an issue, but also we now see pressure management strategies that now exist in the literature, and we're looking to see how that works in practice when Gorgon comes on stream next year. A lot of research on capillary trapping. We know a lot more about capillary trapping than we did previously. We know that the pore volume is more, we're likely to occupy more than 30% of the pore volume, when we really only thought about it was 10%. We know a lot about plume immobilization, how the capillary trapping leads to plume immobilization, improves storage security. A lot on convective mixing and CO2 dissolution. Again, the message is both increase storage security because the CO2 is dissolved in the system and it's no longer buoyant. We've learned a lot about the CO2 subsurface geochemical effects, and one of the key points we've come out that we headline out of this is that CO2 storage is a safe operation if storage sites are properly selected, characterized and managed. And I think that is a very positive statement, and it all is about effective operational management of these sites. And if you do that, then you can be happy that the CO2 will be stored effectively. Environmental impacts of CCS. Now, this is a topic that, again, wasn't even considered in the SRCCS. There are now 12, I believe, I may get this wrong, it could be 12 or 14, controlled release experiments that have either been conducted or are underway. And that's a significant difference in research, significant build-up of research, and some of the major conclusions these are coming out with. And when you also reference, what we've been able to do is reference the information gained from these projects back to natural analog studies. So we have sort of like a comparator with the natural CO2 releases you find around the world from magmatic sources of CO2. So conclusions. we tend to see evolution of these environmental impacts in the form of small isolated areas. So we don't see significant eruptions, we don't see significant sort of surface, for want of a better word, damage if the CO2 expresses itself to the surface. We've also seen that organisms have demonstrated some ability to adapt. So you see some invasive grasses taking over where others have moved out. We also found that artificial leaks have shown that surface expression may be some distance from the source. So it doesn't work with sort of standard convention. You can't sort of predict where they're going to be, and that certainly has been the case in some of them, as actually locating the leaks wasn't easy. And in certain cases where you're looking for leaks from large-scale projects, it may not be that easy to find them. So ground source monitoring is probably not as effective in finding leaks, if they do exist, as more surveillance type monitoring. It's certainly going to be the way forward. Groundwater as well. Again, the work is suggesting the impact on groundwater is more limited than we first thought. And also, again, because it's not going to express itself in the way we first thought, probably monitoring groundwater systems is not a good leak detection option, because in truth it doesn't look like it's going to get there, which is good news in a sense. One outstanding R&D area is we still need better definition of leakage scenarios, and fluxes is still required. And actually that was a point made in the IPCC SRCCS, and we still haven't covered that one, which strangely enough. Monitoring, there's been a tremendous amount of progress on monitoring, and this isn't just short term. We've got next year, we'll have 20 years of monitoring data from Sleipner, so we really are now getting some real long-term data that models and well, that can be calibrated on. Shallow focus monitoring, I sort of poured a little bit of scorn on that earlier, but in truth it did play a very, very important role at Weyburn, when there was a test case that CO2 was leaking from the subsurface, and that was endangering local animal species. And in fact, the shallow focus monitoring, the baseline work done there, showed that that was completely incorrect. One of the issues of leakage monitoring, of course, is if you don't get a result, what does that mean? Leakage monitoring, or surface leakage monitoring, is probably a very good public perception tool. It shows that the operators are doing everything they can to sort of try and find if leakage or surface expression is occurring. But what does zero tell you? Does it give you lots of confidence that nothing's happening? Or, as we saw earlier, are we monitoring in the wrong place? So it's difficult to interpret zero results. So that is something we need to bear in mind in the future. CCS risk assessment. When we started out this 10 years ago, and I was involved in some of the early research work that we did here on risk assessment, we were really using techniques developed by the nuclear industry, and they really weren't fit for purpose. They were leading us up alleyways that didn't exist. But now we have a lot of activity and a lot of good data and proven tools that work and have been tested on real projects, and are now very much an activity that's linked into the development of new projects like Peterhead, Quest, Gorgon, etc. Wellbore integrity still remains a key risk, and it is old wells in regions of the world that have been heavily drilled that are the big issue. A new technical risk has come out, I guess, which has induced seismicity, and that's come really from increased public awareness due to shale gas operations in the USA. But most new projects are building in microseismic monitoring, and to date we've not seen any significant seismic events from any CCS projects. But let's be honest, the scale of injection is relatively small compared to some of the shale gas injections and gas extraction operations and water injection that we've seen these seismic infractions coming from. Mitigation options still remain a gap. I mean, we know what to do if a well leaks, but we haven't really got any ideas. They haven't really done a lot of research in the area if we have a major containment loss. Mitigation options have been modelled, but we haven't been able to deploy them in practice. And in truth, we don't want to be able to deploy them in practice. We want to solve this as a solution underground and hope that we don't need mitigation options at all. Beg your pardon. Economics, well, we know CCS needs to be competitive with other low carbon technologies. Unfortunately, the costs we see in the SRC from the SRCCS days haven't really changed. In fact, they've gone up in certain cases, and that was due to increased prices of steel and labour costs and things. We don't see any technological winner still don't see it. There's no one technology, because the error bands are so great. All three technologies are, the published costs are open, and we're looking at and we do see significant regional variations. Not surprisingly, costs seem to be lower in regions of the world where equipment prices are much cheaper and labour costs are much cheaper. Bio-CCS, focus of interest since the report because of its potential to negative emissions. It wasn't considered in the report at those times. If we were talking about negative emissions, we were thinking about air capture. And again, there's not been a lot of research on that in this area. The IPCC fifth assessment report really covered bio-CCS quite extensively, and it's not a green-eyed monster. We actually do have bio-CCS projects, and the Illinois Decatur project in the USA is one, which is capturing and injecting CO2 from a ethanol plant and inject it into a deep saline reservoir. So we don't see any technical barriers in bio-CCS. The real barrier is accounting frameworks. They don't recognise or reward negative emissions. If you don't account for them, as you don't in the ETS, it's not included, you can't record or account for a negative emission, and you can't sort of award it. And so that is the key area where things need to change. And there's a lot of other complex issues that need to be rolled between the food supply and land production, land availability, water use, energy use, and the climate all need to be resolved. But it does stand out there as an option that's technically proven. It needs the policy makers to move it forward. Talking about policy, really, when we were talking about the SRCCS, we were only talking about the London and OSPAR treaties. And the restrictions in those treaties were quickly removed in 2006-07. That was we made really considerable progress then. We've got now CCS specific laws in the US, EU, Australia, but those cover about 108 countries now. CCS included in the UNFCCC's clean development mechanism, which covers 108 countries. Sorry, I jumped the gun. And so we've seen significant development in policy, but we still have a few sort of areas where we need to move forward. And of course, COP21 hopefully will set an international deal for reducing global emissions of CO2, and CCS will be embedded in part of that as a mechanism that will help achieve that. Public acceptance wasn't a topic before. We've now got an extensive database of published practice, case studies, toolkits. We know how to do it, how to communicate. But in global terms, I guess a general public awareness on CCS at about the same as it was at the SRCCS time. The global public really don't know that much about it. But the efforts that have been made have been put in around sort of actual projects, and we don't see any real issues around actual projects where public acceptance has actually caused a delay or a stop to a project. And interesting, in regions where there is deemed to be significant public issues about CCS, like Germany, the Ketzin project there operated as quite happily and has had good local input and good local buy-in. So if people are educated, people I think will accept CCS. Summary. Science and technology has increased greatly in the last 10 years. We're now ready for large-scale deployment, and we've got several of those projects underway. We're seeing hints now that costs will decrease as leading technologies deployed. If you look at the publications from Boundary Dam, they're talking about 20% cuts in operational cost and 30% reductions in building the next plant in terms of capex, based on their learnings from building the first one. And there's a lot of emerging technologies that do show promise that can reduce the cost further, but they do need scale up and proving at sort of an industrial scale, and certainly in the next 5 to 10 years. We didn't fill all the gaps, and we do want to throw out a challenge to all the readers and authors. If you see a gap, submit an idea and a paper to us. And we're thinking about, in 2 or 3 years' time, a virtual special issue to update this issue already on certain areas where we have looked to fill gaps or significant knowledge has increased again. One gap we already know we've got was wellbore integrity, and we've worked to fill that by a virtual special issue. Again, Stefan Batcher has worked very hard. The 32 papers submitted to the journal, he's reviewed them, and overlap. He's come out with 2 main conclusions, really, that it's not so much the cement is the issue, it's how you complete the wells. And if you don't complete the wells properly, you allow fluid ingress or gas ingress, and that can result in a reduced integrity of the wells. And he shows a lovely graph of surfing casing pressure versus the oil price in Canada. And as the oil price increases, 3 to 5 years down the road, you get the incidence of increased surface casing pressures. And that really he puts down to the fact that because there's a high price on oil, there's pressure to drill more wells more quickly, move on to the next site and get that done, and therefore the integrity of the drilling is not as well as it could be. And that special issue, the virtual issue, you now find at that URL below. And at that point, I'll leave it.
John, thank you very much for such a stimulating presentation. We would like now to address some questions. So if anybody has any questions, John is sat here more than willing to take them. In fact, we have already had one.
Yeah, I have one. The question is, despite the substantial progress made in the last 5 years, are we caught up with the chicken and egg syndrome regard to CCS? And that is that there are not enough plants coming online to prove the technology works and reduces costs, and therefore we can't justify more plants coming online because the technology isn't proven and costs are too great. That's an interesting question. I don't believe we are in a chicken and egg situation. I'd like to be very optimistic and suggest we're not. If you look at the plants that are online now, we have some 6 or 8 plants in the gas processing area. I think we know that CCS is commercially deployable and cost effectively so in that area. 2014 we had the Air Products plant come online in Canada, in the United States, sorry, and the Boundary Dam project in Saskatchewan in Canada. 2015 we've had the Quest project come online in Canada. We've had the Lula project offshore Brazil. 2016 we'll see the Kemper project coming online, the Gordon one I've already mentioned, the Petronova project, the Abu Dhabi project, which is going to capture CO2 from the steel plant. We're hoping we'll see progress on the road project. We're hoping, well, we're confident we'll see 1 or 2 UK projects approved. That'll be the Peterhead Gas CCS project and the White Rose project. So I think we're actually building up ahead of steam. And I think these projects coming on board will stimulate, and we've seen, if you look at the GCSI summary they produce annually, they're increasingly showing a steady stream of projects in the pipeline now waiting to start, and we now see movement in places like China as well. So I believe we're not in a chicken egg. I think we've broken the egg, and the chicken is now a fledgling that is starting to grow, and I'm hoping that that's going to give us the motivation to increase deployment and get us a better handle on cost reduction. And we're already seeing that now. I think we've already seen some strong pointers from Boundary Dam, and we're hoping to see that from other plants as they come forward.
Thank you. A little bit more of a specific question is, why are there not more CO2 capture projects from gas processing? This should be a lower cost option and is very necessary.
That's a good point. Yeah, you actually require CO2 to be in the gas to require it to be processed and stripped, and not all gas has CO2 in it. We certainly in the North Sea, very variable. There's only a few fields in the North Sea that actually have CO2 in them. Onshore USA and Canada, actually, there's a lot of small gas processing plants there, and they're actually largely stripping out H2S, which is in the gas. I think the project we see in Australia, Gorgon, all around that sort of the ring of fire, as they call it there, there's a lot of magmatic CO2 in the gas fields there. And so I see that as a potential area where CO2 stripping from natural gas will be an expansion of that technology in the future. And yes, you're right. I think it is. It's low cost and it's necessary. And certainly gas demand is going to grow up. So I see an expansion in that area, I think.
Okay. The topic of cost now. What are the areas of cost reduction with reference to capture technology that you can see?
Well, capture technology represents about 75% of the overall capital cost. We're looking at reductions in equipment size is really where we're talking about reductions in cost. So the amine plants have large absorber columns. Can some of the other technologies do away with that sort of technology? Can we work with simpler technology, fixed bed technology, or sort of calcium looping technology that actually overall simplifies the engineering sort of side of the technology? And that's where I think the costs, if they're going to come, will manifest themselves. But it's fair to say that we're still building the first generation of capture plant, and Boundary Dam, again going back to Boundary Dam, has shown that there's a lot of redundancy in equipment there that they put on because they were uncertain about how to build it as a first case scenario, and they think they can take those additional sort of redundancy pieces out. There's options there. They used a cement lined absorber tower with ceramic lining. TCM Mongstad is using a plastic liner. That's a lot cheaper. Maybe there are issues with constructing that on site, we don't know, but there are those sort of options that can reduce costs. Certainly there are issues about water treatment. Are we going to measure the sort of levels of nitrosamines that the modelling work has shown us we will do? Possibly not, and if we don't need extensive water treatment plants. There's a lot of sort of costs that will come in as we learn more and more about this technology.
Okay, I think we've got just about time for one more question, and that's sort of, are capture developments largely expected now to be incremental, or do you think there's a potential breakthrough sat out there in the wings somewhere?
Oh, two trains of thought. If you work on a very rapid demonstrate or deployment pathway, a bit like the UK is trying to do, there is a train of thought that you may lock yourself into demonstrated technology, because future investors are going to want their financial risk to be minimized. So you may then be locked into post-combustion capture. But there are technologies out there that show at the lab scale and the pilot scale significant improvements in energy efficiency reductions and potentials for cost. Now, those need to be looked at, and one of the points I was making is what's good in a lab isn't always good in practice. There are engineering issues in scaling some of these technologies up. Can we go from producing an ionic liquid in 1 litre quantities for a year to producing tens of millions of gallons for the future? So there's all those issues that seem to be considered, and one of the things we're doing is doing a regular assessment of where we see capture technologies going. And there are prospects out there, they just have to be proven at scale, and some will fall by the wayside, but hopefully 1 or 2 will stick.
Okay, well, thank you very, very much. And I think at this point we're out of time, and I think we need to thank you and let you go before you lose your voice altogether. And say goodbye to everyone, and thank you very much for attending. Hope you find it very informative and useful.